Hi, I've posted a quick reminder about cross products and how to calculate them. And when we're dealing with vectors, there are two ways that we can multiply vectors together. Now, with arithmetic, these two multiplication symbols, a dot and a cross, both represent the exact same thing. Because with arithmetic, we're just dealing with scalar numbers. With vectors, there are two different results we can get. A scalar result called the dot or scalar product, and a vector result called the cross or vector product. So the way that we'd write the dot product is we'd write vector A dotted with vector B gives us scalar C. With the vector product, A cross B equals vector C. Now the big place where the cross product is different than regular arithmetic and with the dot product, both of those allow us to flip the order of multiplication. We still get the same result. With the cross product, if you flip the order, you end up getting the negative of the result. The direction changes if we change the order of a cross product. So the simplest cross products we could do are just with the unit vectors. So the cross product asks the question, what is the area created by a parallelogram made out of two vectors? Well, with unit vectors, the size of each vector would be 1, so if they're in the same direction, then you try to make a parallelogram, you get a line. And the area inside a line is of course 0, because it's one-dimensional. Now, if you have right angles, then the area that you would get for each would be 1. But there's a direction associated with the cross product. And we need to use the right-hand rule. So if you use your modified COVID-19 Star Trek salute, you can line up your hand in whatever way is comfortable. So if this represents the x-axis, we call I hat, and these fingers represent the y-axis that we call j hat, our thumb is going to point in the direction k hat. So x, y, z axis. I hat, j hat, k hat. Now, if I reverse it and go j, I, by the right hand, I would have to flip things around. J, I, minus k. That's really cumbersome to try to dislocate your wrist. So remember, whatever digit you pick for your right-hand rule, you can start with 1, and as long as you go counterclockwise as you look down at your hand, you're going to get the right order. So to do the reverse, I could say J, cross I, minus K going into the board. Now, if I have X cross Z, so I will start with the X-axis, Z-axis coming out of the board, I get the minus Y-axis, minus J. So J cross I we already covered is negative K, J cross J is 0, J cross K is going to be I. So there's a little mnemonic to remember the unit vectors. If you go I, J, K, all throughout, pick a starting letter. Whatever you start with, if that's your first, the next letter is your second vector, the third letter means it would be positive that third letter. Now, for the negative vectors, it's reversed. KJI, pick one to start with, go on to the next one in that KJI sequence. That's your cross for your second. You get a negative third vector for the result. So, we normally write out vectors as saying they have x, y, and z components. So to calculate our cross product, we could think of this as a distribution problem from algebra, where we take each piece and multiply it by all the other pieces. So since vector A and vector B have 3 pieces, we end up getting 9 total terms to sum together. Well, the multipliers of our unit vectors are scalars. So we could just pull those out in front and then evaluate the cross product of the unit vectors. So our x terms, x cross x, 0. X cross y, well, that's going to give us positive k. I cross k, x cross z, that gives us the negative j direction, the negative y direction. And we could apply that process for each of those terms. So all of those terms I've written on the diagonal, they go away. They're zero. And what we're left with to calculate the cross product, A cross B, for our x component, we take the y component of A times the b component of z minus the z component of A times the y component of B. For our y component, j hat, we get the z component of A times the x component of B minus the x component of B, or x component of A times the z component of B. And our final term, which is really the term that we use most often in physics because usually we're just working in 2 dimensions, so a cross product in a 2D plane ends up just in that 3rd dimension, which we usually use as k hat. So our x component of A times our y component of B minus our y component of A times our x component of B gives us our component of our cross product in the k hat or z direction. Thank you for watching.